Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and today we're going to talk about more on testing these little mini free energy devices, the SSG motor Energizer, and this is the new kit, as we've talked about a little bit already. So what I want to do today is focus on where we begin. And I want to clear up some misunderstandings that need to be addressed. Now, this isn't going to be anything controversial in this video. So what we want to do is look at batteries. What kind of batteries? How do we evaluate our batteries? Because if we're going to use one of these systems, half of the system is a battery. So you're going to need to know how to evaluate what batteries you have, what their capacity is. And I want to get into some details. Actually, I want to jump right into one point before I forget it. So in evaluating a battery's capacity, we're going to have to do measurements. We're going to have to figure out how to determine where it's really at. Now, you'll find some information, of course, on the battery itself, or from wherever you bought it. There should be some information about the specs. And so, how do we determine what amp hour means, and how do we evaluate that we have the amp hour in the battery from the beginning when we bought it? Does it really have that capacity? And if we're going to evaluate an energy device that uses batteries, and the batteries are determining the proper understanding or the evaluation of the battery determines the efficiency of your system, then we really need to know that first. And I've worked with tens or even hundreds of thousands of people around the world over these last 20 years. So I think I know a little bit about where people are at, both today and 20 years ago, with those things, those matters. So I'm going to give you an example. I was invited, over 5 years ago maybe now, down to a certain place, will not mention, some of you will know who I'm talking about, and there was a guy who had invited me to see his systems, and I went to see what he had going, and the only thing he had going was actually my motor, one of my bigger motors. And he said, "Look at this, I'm going to show you something, Rick. Something that you don't even know." Well, I didn't see anything in that case, in that way. But what I saw is he showed me how fast he could charge his batteries. He had some golf cart batteries, and boy, they were charging up in seconds. So raise your hand, how many of you know what he was doing, or what he was doing wrong by charging up a relatively large battery bank, golf cart batteries, very quickly? And he was really convinced that he had something special going on. So I realized that he didn't. I knew exactly what was happening, but I wanted to see everything he wanted to show me before I commented. Anyway, I don't think I ever did tell him his error there, but I will tell you now. So maybe some of you have seen the same demonstration. Maybe not there, but in some video. So this is a way of what people do to cheat and make you think they've got something special when they don't. So I want to clear up this point before I forget, even though it wasn't going to be in the order that I was going to share it, but I have to roll with it sometimes. Anyway, so you have a battery that should be taking a certain amount of time to charge up, and it charges up in seconds. So it goes from, with a voltmeter sitting at, let's say, 11 volts on a 12 volt battery, and suddenly you got it going up to, within minutes, maybe 13 volts. So if you have a battery that's at 13 volts and it's a 12 volt battery, what does that mean? So there's going to be a couple of things we want to look at in this video about how to evaluate voltages. Voltages under load, voltages under charge on a battery, and resting voltages. This is very important, and very few people are making distinctions here on these matters. And so your average person who doesn't know electronics or very much, and he wants to dabble with these energy devices, they need to know the basics. So in the case of this person who was mistaken, they were both looking at the voltages under charge, and they were also looking at the voltage under rest, but making a critical mistake. So first of all, the voltage under charge is a problem if it's pulsing, or even if it's not pulsing, if it's just DC charging on a battery. The problem is that the voltmeter is having two different voltages that it's having to deal with. It's dealing with the battery voltage, and it's also dealing with the input voltage. So if the voltage on the input is greater than the actual voltage on the battery, you will see the voltage on the input, and the battery is being pushed up to that voltage, but it's not resting at that voltage. Once you turn off the input, then you will see the battery start to come down. Now, this isn't really, people aren't really ignorant of that in the most part. When you have a pulsing input, it becomes even more dramatic, as that pulse can be really high voltage. So I can pulse a battery that's 12 volts with 300 volts. In fact, we're doing that with this little motor, because you'll see a spike over the battery voltage, and if you look at an oscilloscope, you can actually see that spike, unlike you can't see that with a voltmeter. So in that case, the voltmeter is doing its best to give you some kind of average voltage between the two, and then you can see it jump around if it's really pulsing, depending on what kind of pulse. So, but what I want to focus on beyond that is when this person I was referring to showed me, after they stopped my motor that they had bought from me, and they were looking at this battery and saying, look at that, and the voltages were higher. And I guess they were trying to impress me, but they didn't. They did the opposite. They showed me that they didn't know what they're doing, because actually what it showed was a battery that was really, really sulfated and had no real capacity left in it. And so maybe they had the golf cart, which was maybe 225 amp hour battery, actually being maybe only 1 amp hour or less. That it was so bad that the voltages went up, and they actually stayed there. So that was a pretty bad indicator. So let's get more into specifics of what all this means. So I think we're going to go over, we'll get to those points, but I wanted to start that off. We're going to go over what we're going to do to evaluate the system and our batteries. The first thing to do, like before we start evaluating the system, we're going to go into the details. So the first thing we want to do is get a battery that's brand new, and preferably one that is really brand new, not merely bought at the store, but one that hasn't been sitting there for a long time. So if you can find a date stamp on a battery, sometimes, like if you find an Amazon battery like this, a battery from Amazon, you might not have any indication of how old it is. And if a battery sits, it's going to lose its, people will say its life, but its capacity. And it can sulfate up or have some kind of degrading process in it. So what we're going to do is take a battery. In this case, we have a sodium battery. This is interesting because it actually functions as a 16-volt battery. But we want to form this battery. Now, forming batteries is not something you think you need to do, but for this experimentation, we're going to show you it's similar to forming a electrolytic capacitor. Electrolytic capacitor that sits for at least 8 months or longer will need to be reformed, and that includes your various inverters, amplifiers, and various equipment that have capacitors, like your power supplies, which we'll look at in a minute, which is right on the table where the camera is here. We're going to look at that. So if this device is sitting for some time not used, then these capacitors can become unformed. They need to be formed, and we've talked about this, I think, recently in previous videos, where you need to prevent this capacitor from getting hot and potentially blowing up or being damaged. So when you apply a DC voltage across, in this case the battery, but in the capacitor case the capacitor, and you apply a very low current and slowly charge that up, and you do it in stages, then it can properly, you can call it self-healing in a sense, but it's quite important. It's not something that people really know about too much anymore, but it was very common in earlier days. So we want to do this with a battery now. So we take a brand new battery and we discharge it. We figure out the amp hour rate. So if we have a battery that is, say, 1 amp hour. Well, we're going to look at the ones in a minute. This is a 6 amp hour battery, and it says 12 volts, but it really is higher than that. But the ones that we're going to be looking at are 4 amp hour batteries, and they're the sealed AGM type. So if you had a 4 amp hour battery, we want to discharge it down to fully discharged. Ooh, that sounds bad, Rick. You don't want to do that. So this is going to be the first misconception I'm going to explain here. There is nothing wrong with deeply discharging a battery, even down to 0 volts. Yep. And I'm going to be the first one you ever hear that, probably the last one. But we do it all the time. And we'll get into that type of deep discharging later on in what we're doing in this kit here. That will come into view, into focus later on when we get into a little bit more advanced matters. But now we're going to focus on deeply discharging it down to fully discharged. And that's way higher in voltage than down to 0 or 1 volt, say. So we're going to go to 10.5 volts on a 12 volt battery. That is either lead acid, sealed lead acid, or AGM or gel, however you want to look at those groups of batteries. We're going to discharge any and all of those batteries down to 10.5 volts. But the real question is, and this is not addressed so many times, people don't know the answer to this, but how are you going to determine 10.5 volts? Under what condition? Under rest? Are you going to keep discharging the battery until when it is under rest is 10.5 volts? Or is it under some particular level of discharge through a load? So what kind of load will we determine to determine when a battery is fully discharged? So if you have a fully discharged battery, means when you are discharging it at the C20 rate, so what's C? Right? That's the first question. But while we're discharging it at the rate of C20 and we reach 10.5 volts with a voltmeter across it, that's when we are fully discharged. So forget what everybody else is saying. You can look that up on Google right now and see that that is correct. Despite people saying other voltage is much higher than that. When you're using an inverter that converts AC to DC, that runs off of converts DC to AC, that means when it's running off of a battery and the 12 volt battery reaches 10.5 volts, then most inverters will shut off at that point, considering that fully discharged. And one of the reasons why they also turn off at that point is because they are there is not any real capacity on a conventionally charged battery lower than that point. So therefore, if you run anything lower than that point, it will just take a dive. The curve will just go like this, go. Now that will happen more or less depending on how fast you are discharging your battery. In other words, how big of a load. So we want to look at it being at C20. C20 meaning now that over 20 hours you're going from a fully charged battery, which is typically on a open flooded lead acid battery, 12.65, let's just say. Maybe it's 12.6, maybe it's 12.7, right around there, 12.65, let's just say. And you're going to discharge this battery for 20 hours so that it reaches 10.5 volts. So we have to determine what load do we have to put on it to be able to achieve that. And is our battery really in new condition? Is it really the rated capacity that it says on the label? So if we have, again, a 4 amp hour battery, which is what we're going to do and show you, which is what I just did the other day with these batteries, and we want to determine, how do I determine what the C20 rate is? Do you know the answer? If you don't, and you're already evaluating the batteries or making some determination about some of these systems, then you're flying blind. You're just guessing. So what happens is, you're going to take the basic resistance R equals volts over I, volts over current. So now we have to determine what resistance is. What's our voltage? So our average voltage over this time is going to be 12 volts. 12 volts, 12.0 is not fully discharged, nor is 11.8 fully discharged, as some people say. In fact, it is 10.5 volts under the 20-hour rate of discharge. So now, and so what will happen is once you take off the load and it's 10.5 volts under load, take off the load, then you will see the voltage will go back up a bit. But it's under that load that it reaches 10.5 volts. So we're trying to figure out what resistance am I going to put on this battery to discharge it for 20 hours to get that 10.5 volt reading after 20 hours. So we divide the voltage, the current. We are the amp hour already, right? Say it's 4 amp hour. So what is the voltage over, what's the answer? Can you answer that question? So the answer is 12 volts, 60 ohms is the resistance. So what I'll show you, so here's a big resistor. This one happens to be only 8 ohms. And this one is a variable resistor. It's a dial here that I can turn, and I have set for 60 ohms. So this 60 ohms over at 12 volts average is going to give me how many milliamps? So I have, oh, I was doing something else here, but so we're going to get 200 milliamps is what we have with those 4 amp hour batteries. I actually wanted 2 amp hour batteries for this test, but I didn't have any options there. So I'm going to discharge it, which I've already done, over 20 hours. Well, it turned out that it took 22 and a half hours to get down to the 10.5 volts. So I took an estimate and determined that. So what we're trying to do right now is determine our time scale. How long is it going to take to charge up the battery and discharge it? But we want to still determine the actual amp hours of the battery. So in this case, the batteries were discharged, the one battery so far was discharged over 22.5 hours at 60 ohm resistance, which then, while I was doing that, I measured on average 200 milliamps. So at first it was a bit higher than 22 or 200 milliamps, and then as the voltage dropped, so did the amperage. So then it became down to 180 milliamps at the lower voltages. So on average, you're not going to keep that exact load amperage. As the voltage drops, so as the amperage will drop. So we're going to get approximate value, but we're going to keep everything the same. Next time around, we're going to look at that. And then we have to do this several times before we get stability here, and that's what we're after. We're trying to do a controlled experiment here, and we don't find people understanding what that means anymore. We don't find it in the scientific world, which is often very compromised in looking for they're stuck in a state of confirmation bias, and so they are changing the numbers intentionally to get what they're after. So it's highly dishonest. For other people who are impatient or ignorant, they will be guessing, and they won't know how to evaluate what they have until they do what I'm talking about here. So what we're after is to try and determine the actual amp hour of the battery, and also the capabilities of the system, what we can do with this, and what time periods we need to allot to measure all this. So we're talking primarily here about the very efficient way of using these batteries, which is at the C20 rate. So there is another factor to consider. As we discharge or charge this battery faster, we get less efficiency out of it. And we have Puchardt's law that pertains to that, which I won't get into. You can look that up on your own. So if we've determined that our batteries are slightly more than 4 amp hour, then we have to adjust either our resistance to make it 20 hours, and you can plug it into the equation and find out what it then means. What is the resistance difference then? Now, I'm not quite committed to changing that yet until I do another run. I'm pretty much going to keep it as it is now that I've started. Because what this test will bring about is we want to see the changes in the battery efficiency next time around, and for several times. What does it take when it's reaching a certain voltage and we discharge it down and we keep going from that repeatedly? What's going to happen to the battery? Is it going to change? And that's actually what we're looking for in the first experiment here. But the main thing to do is to get to the point where we can understand where our battery is really at. So it's going to take several cycles. If we're wanting to do science, we have to take the time. And I rarely see anybody willing to take the time. Now, there was just one good soul from the past who just wrote on my channel here about having all of his stuff erased just as he had crossed the finish line on those groups so many years ago, and he was excited to see what we're doing now to continue on after, since 2013, I believe all those emails were erased. Anyway, we're going to go back and continue off where we left off. So the point is, we have to establish a control. We have to establish what we actually have in our possession. What are the tools? What are the means we're going to use? So we have a hypothesis in our mind, and we want to try and confirm or disprove that hypothesis. Or we're just not sure what to expect, but we have to change one variable at a time only. after we have a baseline being we have established what we have, and then consider how that changes for better or for worse. So all this is very important, and it's part of the so-called scientific method. So we're looking at how to determine the amp hour of a battery, how then to go from there to discharge our battery over the C20 rate discharge, which is a 20-hour rate of discharge. And then what resistance we needed to do that. And then if we have to adjust because our battery capacity is higher or lower than that actually, then we'll have to recalculate either the resistance or just take more time with that resistance to see where it ends up. So now you can also do, say, the C8 rate of discharge or the C5 rate, but for these experiments we want to do the C20 because it's more efficient, and that's what we're after here. It's a reasonable rate to use. So the battery manufacturers will often have two different rates: the C20 rate, maybe and the C5 rate or C8 rate. So generally, you can have two different numbers that they'll give you the time it takes to discharge them at that rate, and the amp hour it will have, or the minutes, the capacity, reserve capacity. So I have to deal with these numbers all day long with my customers and doing evaluations of systems that they want to use batteries with. So now we're going to get into the charging rate. So once we've determined that the battery is discharged at 10.5 volts under the C20 rate, and we discharge it to that point, what am I going to do next? So I'm trying to decide on how to still present all this information in this kit book, because I'm going over the old recommendations that were given on the groups. Now, I stopped being the moderator of my groups for some years, and then other moderators then changed the information, and so that it wasn't really the best information as far as I can see right now as I'm going over the details. So now what people were saying, primarily Bedini, was the battery was dead at 12 volts, or it's fully dead at 11.8 volts or something, maybe 11.9 volts, but that's just not the case. So if a battery's standing at that voltage, then it's pretty dead. But if it's under load and you measure that voltage, that's different. Now, in my meetings, I'll always tend to show a demonstration of a big battery, like 2 golf cart batteries in series to make a 12 volt battery, 2 6-volt batteries, and I'll run a 3,000 watt load across that, like these big lights, 3,000 watts of lights. And then you'll see this battery dive, and then the inverter will shut off within minutes. And so I'll ask the question, and I know I've said this in the previous video recently, but it's important to go over these points bit by bit here. So I asked the question, is that battery discharged? Is it discharged? And some people say yeah, and others will say no. And I'll show the voltmeter. The battery looks the same voltage than when I had just run it minutes prior to that. It's because there's a big voltage drop. And so the voltage drops below the inverter cutoff point. So if you have a, maybe not as extreme discharge, but say you're discharging it, you know, over an hour, and it's like the C1 rate, you're full, like you're down to this so-called 10.5 volts over 1 hour. It's still not the right measurement to determine that it is fully discharged. So what happens is when you disconnect it from the load, even though it had just read 10.5 volts, it will bounce back because it's not discharged. It's only partially discharged. So we have to be accurate about our words. But in this case, you could still be wrong on all that. For what we're doing is we're just trying to determine the efficiency. And we have to do that by keeping everything exactly the same. So if we have a low voltage termination point where we discharge to, and then we go from that point after a set period of time, maybe instantly we charge it back up, or maybe we let it rest a bit. I'm going to talk about that in a minute. But if we go then to a high point where we stop charging it, we have to do the same thing each time. So we're going to do this 10 times to establish where we're at. And also we're going to see the changes. So if for some reason it gets shorter or longer, we want to notice that. So you're going to see at the very beginning there's going to be a little bit of changes, but then we want to get to a point where it's stable, that it's not really changing anymore. And that's where we know where we're at in the system. Then we know where we're at with our batteries and how the system's working upon the batteries. So these are all very, very important points. It may seem obvious to some of you, but the whole thing about these exact numbers that we're going to do is very important here. As I go over this, I realize the mistakes in some of the methodology and the understanding. So I'm going to tell you after all these years, well, I'll call it the truth, but depending whether you think I'm worthy of listening to and whether that's the truth, it's for everyone to determine. Anyway, the point is there's things that were said that aren't actually correct according to the way I understand things. And let's go into those. So when we go into now, there's a couple of things I want to say on the side points here that are important. So after we get past this DC charging of this battery or the other battery, like I did, is I put a power supply on that battery. So I discharged it first with the load that I expected to discharge it over 20 hours, as I mentioned. Now I was going to charge it up to what voltage? Now get this, 13.5 volts. Okay, this is a big point. But what did I do to do that? I set the amp meter or the power supply. These ones aren't very correct in, I'll put it to 13.5 termination point, or the 13.5 volts is going to go across the battery, and that's the maximum. And then the amperage I set to 0.1 milliamp. Now the reason I did that is because it automatically does it higher. But I'm going to slowly charge this battery up that's been discharged so that I really form the battery with DC. Now we actually want to unform it from DC, but first we want to fully form it. We don't want to do the pulse charging or anything on it until we've made it clean. And so what's going to happen is it will, on my particular meters or power supplies, even though I have it set for 0.1, I was just trying to do the minimal, it will still put about 50 milliamps into it. And so I let that go for a whole day or so until it basically came up to the 13.5 volts. I don't want to go higher than that. And the reason is, so forget Peter Lindemann and forget John Bedini, who keep telling you over the years you had to go to 15.5 volts. Well, you don't, okay? Don't do it. Save your batteries. Remember, I'm the guy who always said battery longevity is the first premise of my company. And others are battery killers, other people. So, there's no point in charging a battery after it's fully charged, right? You don't have to charge it. 13.5 volts over a 12 volt battery is fine for a flow charge. So your alternator, you're going to turn down your alternator voltage regulator to 13.5 volts if you want to keep your battery from shedding or off-gassing needlessly. So that's the acceptable low end of an alternator. And depending on your applications of all your accessories, what I'm suggesting is you change your solar chargers and whatever other battery chargers to no higher than 13.5. So what we found in our business, of course I deal with batteries all day long, all over the world, and you have two different, same battery in your alarm charger, your alarm system, that has a standby battery if the power goes out. As the UPS system, same battery. And yet one's a battery killer and the other one is not. The alarm system has its voltage at 13.7 volts maybe. This is the ones that we found when we started doing this. We have an alarm charger for this very purpose that allows you to keep your batteries for good. And then the UPS system, on the other hand, has a voltage much higher. So whenever your power goes out, you have nothing left of that battery after not very many months. It is a rip-off. It is criminal to me that that industry has been doing that. So there you have it. The one is like your alternator in your car that's cooking your batteries to death on purpose, so you're replacing your batteries every 2 years. And then they're giving you sealed batteries, so you can't even put water in them. And that's on purpose. And those sealed batteries, remember, are only supposed to be charged at like 2 amps. I remember 35 years ago in the dealership when I started out as a mechanic, at 16 years old, I watched where my instructions were on the battery itself, 2 amps only. This is a battery, a starter battery, that was going into an Audi. I worked in Volkswagen, Audi Volkswagen. And so that's what those batteries are useful for. Don't charge them fast. You don't off-gas them. And certainly don't leave them charging when they're fully charged. So we're not going to do that here either. We're not going to overcharge the batteries like certain people were telling you to do. Now it's not so critical with the pulse charging as it is with the constant current. The people aren't even making the distinction between the two. So I'm trying to clear up some misconceptions here again. So we are not going to charge the batteries over 13.5 volts. Now again, that is based upon a certain rate of charge, right? And the difficulty is in determining what the actual battery voltage is. So this is where we have to make some decisions here. And I'm going to talk about two different things, so don't let me forget. Rest periods are important for this research and what we're doing with this kit and other kits like it for a lead acid battery or similar batteries. And also the efficiency of how high do we need to charge a battery in order to get the best efficiency out of it. That's so resting and how high and how low we're going to discharge the battery. So I want to set the record straight of what I've been doing and many like me have been doing over the years. So first of all, and I'll go over all these details much more in the kit, right? But I want to at least give everybody this information so that they know, to put everything in perspective of the past, of the things that we were doing with this SG kits, these SG kits, the schoolgirl kits. And then, so they were not deeply discharging them because they were afraid. They were told by certain people and in industry that if you deeply discharge a battery, you're going to damage your battery. That is factually not true. It is only true in the context of DC charging, and so which is bad for your batteries, okay? It's not good ultimately because you still have to replace your batteries when you do that. So we've had batteries come back 20 years ago that are still in use, and they've gotten better over time with what I'm saying today, right? Now I've dealt with the top people in industry in various countries around the world in these matters. So I'm not some hobbyist on the subject. So anyway, what we've done in the more advanced systems that we'll get into in this kit, we will actually discharge the battery right down to 0, or like say 1 volt. We'll put a light bulb on it and deeply discharge it until the light bulb goes out. But then we'll charge it back up. We won't let it sit there for days or weeks or whatever. We'll charge it up. On the other hand, on the other side of it, we won't need to fully charge the battery in order to get the greatest efficiency. So there's windows, just like capacitors. Your electrolytic capacitors, for example, they have certain windows where you want to operate in that are the most efficient. You don't want to necessarily discharge them completely down, or you don't want to fully charge them to their maximum capacity or voltage. So you want to work within a window, and the battery itself too is that case. Now with the Teslas, and I know very many people that have Teslas, and we put together a Tesla, like we literally made a 55 Chevy into a Tesla. Now I wasn't responsible for that, but I was overseeing it to some degree to keep people safe. So I've worked with a lot of people that have Teslas, and we've evaluated the systems. They're telling the owners to run them from 80% charge to 20% discharge and work within that range because they'll last longer. There you go. And those are lithium batteries, lithium ion. So the truth comes out more and more about the details matter. And the faster you charge, the faster you discharge too, is going to affect even those batteries. So I work with all types of batteries now. So when it comes to these lead acid batteries, we're not going to charge them to 100%. But get this, the batteries will change over time. So that's going to be part of the experiments here, that you're going to see that if a lead acid battery normally sits at 12.6 or 7 volts, I'm talking about the flooded type, not the AGM or whatever that can sit higher. So say you have your flooded lead acid battery start from brand new 12.6 volts, let's just say that. After several of charges with our systems, our Renaissance Charge battery chargers, or even with this type of system here, you will find the battery will sit at a higher voltage pretty quickly, like say 12.8 volts. And that's resting. That's not a surface charge. So then after months, like when I've had 3 electric cars that we've built. I did a Honda, I did the Porsche, and more recently we did the Veloster that you've seen you haven't seen the Honda in my videos. But those batteries got better and more capacity over time. So after about 8 months, my batteries, if you consider 12 volts of them, were sitting at 13.3 volts. A flooded lead acid battery that is golf cart, Trojan T105s. Right now I have the interstate ones, Costco ones that are 210 amp hours. And they've gotten better over time as we've used the proper charging. So then what I was saying is, just a little bit back, that we don't have to fully charge those batteries if we want to get the maximum efficiency, the right window. But if we work those batteries to the higher voltage, eventually they rise in their voltage and they have greater depth of discharge capacity. So, and I'm saying these words that I'm saying right now many times throughout the day to various customers, that you can gain a capacity both on the upper end and throughout the whole cycle of the battery, the whole discharge. So we found that after 35 cycles, we had 70% more energy in the battery than the exact same identical battery charged with other chargers. And that was a graph that we had years ago, about 20 years ago, almost. So you can imagine now, we're starting, say a battery starts at 13.3 volts, and now I can discharge that not only to 10.5 volts, and it doesn't just take a dive. Now it's more like a linear drop. So you don't have the same kind of characteristic curves. Now you have capacity at 10.5 volts. Then you have capacity at 10 volts, 9 volts, 8 volts, down, down, down. So now if you were to actually, we don't measure beyond 10.5 volts, because that's the standard. But if we did consider that, if we really deeply discharge that battery, now we could have up to double the total available energy capacity of an identical battery that wasn't charged that way. We've seen that time and time again. So, for example, you're running lights that can still operate at lower voltages. That's great. You work with a boost system, so that will just hold that voltage higher under the load while the battery voltage is dipping. So for example, my electric cars. I was part of the electric vehicle club in Spokane, Washington, and some of the people had my charger and others didn't, the electric vehicle charger. The ones who didn't, sometimes they would just drive too far and they would have to get towed home because it just dropped. When I started, what I would see looking at my voltage, it would be a slow, steady discharge, and I could know exactly how far I could go, and it would just slow down. This was just when we were doing the conventional motor in there, and I was trying to evaluate for the battery charger experience to know what my customers were experiencing. So we did that as an experiment. It was a long-term experiment. So what I'm saying is, we can deeply discharge the battery without harming the battery over time, and using this very little motor generator here, Energizer, it will do the same thing over time. It will change the battery fundamentally. Now we'll change it in other ways that the battery chargers that we have don't do, and that we'll get into later on in another video, or you can look at previous videos that I've done on the subject. So now the battery can be deeply discharged, and there's an operating range that is optimal to use the battery in. I'm not worried about deeply discharging the battery with the right type of charging, but I don't necessarily want to push it all the way up to 13.3 volts. Now under charge it's going to be higher than that, but at rest I don't necessarily need my battery to, like after you take away the charging, at rest to 85%. So it just so happens that if I increase the voltage of my battery from 12.6 volts to say 13.3 volts, like I'm saying, now 85% of 13.3 could be 12.6. So once you've formed this battery and brought it up to that place, you don't necessarily need to fully charge it. You might want to do that once in a while to work the battery, and that's what we do. We actually, when we put our 3812 charger rejuvenator on our batteries, we will deeply discharge them to 8 volts and up to fully charged, and you can see that go way up in voltage, but we don't have to fully charge it. So when we're doing a over unity type of system, we actually found that the last 10 to 15% of the charging was not the best use of the energy. In other words, work within the other window below that. Now again, you can go as low as you want. It doesn't matter to me, and it's not going to affect your efficiency. But it may affect the operational, like you don't necessarily want to go all the way down to really low voltage when it's functioning as a load battery, where we're loading it down. It may be a certain ideal, but the charging termination voltage is what I'm talking about here. So I will get into that in this SG kit here, as to what I'll do, but the key thing is it's not about what I'm doing that you have to copy it, and that's where I would depart from other people that said you have to do this way exactly. There'll be many variations that people will do. Of course, certainly I've done many variations. I've done hundreds and hundreds of different models of motors, different types of motors too. I can confidently say more than anybody who's ever done these things. I've done more. I've spent the last 20 years of my life making numerous models. But I've learned from others at the same time. We learned together those 20 years ago. So I hope to bring that back, open up that. So again, the points here are that I'm recommending you like you form the battery first. You try and get a new battery so you don't have to desulfate it with our chargers. Oh, that brings me to another point. So this was the charger that we still sell. This was one of our most commonly bought chargers. It's the RC1AU, and it does 1 volt to 24 volts of batteries, series or parallel, up to about 2 amps. And it has a variety of features, 9 power levels, or 8 power levels, sorry. And then it has, like this was doing the NiCad batteries, nickel metal hydride, nickel cadmium batteries initially, and the small lead acid batteries. We do not recommend charging lithium batteries, even though we can, and some of our customers have done that, but it's too dangerous. Putting lithium back into a battery management system is asking for trouble, and I know people are going to catch things on fire, so I cannot recommend that. So if you have batteries that are used, we recommend using our charger to bring them back. And in this case, we're using the smaller ones. We have up to forklift size batteries of chargers. So Renaissance Charge is a company. r-charge.com or .net is the website. So again, what we're talking about here is forming the battery first, then discharging it at the C20 rate, then determining, so that's going to be discharging it to 10.5 volts. For now, we're going to do 10.5 volts for this opening experiment, which you don't have to do that experiment. If you're going to get the kit, you can do whatever you want. But that's how we're going to start it, and that's what we were doing on the list. The monopole and other forums. So then, if that's the termination voltage, 10.5 volts under that load, then the charge rate will be depending on the sweet spot of this motor. So we're looking at, right now, you'll see as I bring the camera over there in a minute, that the motor is running at about 100 milliamps, 120 maybe, and it fluctuates at night. Things change than during the day. So this is a wild animal, a beast that cannot be tamed. And we'll get into the more advanced and intermediate levels, and that does not include what you saw in those other booklets that didn't come from me. This is other information. So then what we are looking at is going from 10.5 volts up to what you choose, and then it will be at somewhere between 70 milliamps, probably is about the minimal, and then up to 200 milliamps. Now, I was running it at 800 milliamps, but that was not efficient at all. So then you can determine through other experiments, which we'll get into, what is the sweet spot. Now it takes time, so we want a baseline to start off with, charging it up to a certain termination point, which I'm saying 13.5, no higher than 13.5. So if you're going to push it hard and have higher milliamps charging rate, now again, this is not charging it with amps though, I'm talking about input amps into the motor itself from the input battery. So you'll see right now the input power supply is set where it's holding the battery at 108 milliamps at 12.47 volts. So a little bit low, needs to go up a little bit higher to match. It's slightly discharging the battery at this rate. So I have to still do my adjustments. So we have two of them, and I'll explain that in a minute, that are running right beside the camera, and I'll show you in a second. So then we are going to terminate that at the hourly rate that will bring us to what we consider fully charged. So we have to then determine, since we were discharging at 200 milliamps and now we're charging it just above 100 milliamps, that it's going to be like 48 hours, somewhere around there, before we reach up to that point. It's a long haul. So these batteries are about twice as big as this system really needs to do this 20-hour rate. Now you could charge them faster, but we're after the best sweet spot right now. And that has to be determined with other factors. So that will be three things, not two, like they were always saying to you, two things. There's three things here, three variables, not two. In fact, there could be more than that. So let me say them for now. It's not just how fast the input, like how efficiently you're running the input battery to run the motor to charge the batteries. So we're looking at the charge rate, how fast the charge is going up, and how fast the input battery is discharging. In this case, we're leaving the power supply on there, which is not the efficient way. So here's another point. A lot of points in this video. We don't want the power supply on the battery for the ideal, because, this is a side note now, because the power supply cannot receive excess energy into itself like the battery can when the battery is by itself. So the energy goes in all directions. It goes into the charging battery primarily, we're interested. It goes into the input battery too, and it goes into the environment all around, which I showed with the EMP coils in that one demonstration, that we get charging out of that. And there's all sorts of extras that you'll see in this kit. And I've talked about them in videos already. So we are just doing one thing right now in this first experiment, and we're focused on the charging battery alone. We can focus on the efficiency of the system prior to doing this, but I already know what I wanted to do, so I'm just showing you one of the major experiments here. And so we are going to look at what happens with each cycle to this battery, and that's it. After that, we get into the input versus output into the system. Now we're just looking at the system, what's happening in that battery over time, because we want to know what our battery is. And we want to change this battery to a negatively charged battery. And that whole subject is another thing to get into in another video. We've done videos on that subject already. So we're going to change this battery for good. Now we can change it back to a positively charged battery. In fact, I had already made this a negatively charged battery to a minor extent. And then I decided I'm going to reform it by putting the positive charge into it slowly, like that, and change it. So I'll just say this in passing. When you're negatively charging a battery, and you do this over months, to change it back to positive will take about the same amount of time to convert it back to positively charged. It is not harming the battery. And one of the things, I guess I'm jumping into something off topic, but one of the things that people must understand is when they negatively charge a battery and they let it sit for a long period of time, it will deeply discharge down low voltage. And people will think their battery's ruined because they'll try and put a positive charge on it and it doesn't respond. But what's very fascinating is if you keep doing it for a long period of time, it will eventually pick up and it'll be back to normal like it was before. So what's the advantage of negatively charging a battery? Is it can quickly charge and it continues to charge. I said I was going to get back to the rest period. So after you deeply discharge this battery, or you charge it up relatively quickly, you don't let it sit like that. But when you fully charge this battery or partially charge it, you can let it sit and it continues to charge on its own, more than what you find with a conventionally charged battery. So it can actually keep on charging once it's been done for a while for a whole day. But when it stops charging, it starts to discharge. So this type of system is, if you don't use it, you lose it. This is not for storage. What I showed in the previous videos, just 2 videos back, or was it the last video? Yeah, 2 videos back when I showed this fan here running. That particular system allows you to have it as a storage battery. That's fine. It's a power wall in that case. This particular system, that battery that's being negatively charged has advantages, but it has the disadvantages that it doesn't store the charge, it doesn't hold the charge for very long. It continues to charge, so the rest period, incorporating the right type of rest periods into this, makes this way more efficient. So if you actually had 2 or 3 batteries rotating out, one gets charged for a bit, the other one's continuing charging on its own, and then a third one at different intervals coming back into the system, boom, you'll have even greater efficiency out of the whole system. So these are things that people don't have the patience for. There's been only a few of us over all these years that have really taken the time to explore that and engineer this technology. And so all of it's very relevant and very important. So we're going to touch upon those things that you don't find elsewhere mentioned anywhere. Okay? Nobody is teaching this at all. No matter how much their books tell you that they're advanced, they still don't teach you these things in them. So details matter. So then we were talking about the termination voltage. So once the battery, say we go and terminate at 13.5 volts, that means we're looking at a voltmeter until we see the voltmeter. Now what we're going to put in there is an amp meter, an analog amp meter. I'm going to show you that in a minute. And there is one that is an option that you can get with a kit. And we're just going to limit it to 200 milliamps because we don't really see running this thing at higher than 200 milliamps. Input energy I'm talking about. And we're going to leave that on the input battery, not the charging battery. We don't want to leave the amp meter or any voltmeter on the charging battery. You can periodically use it. Now this clamp amp meter is not good for that. It's not going to see amperage on the charging battery. Even on the input battery, this is not really recommended. You want an analog meter. And the whole thing about putting an amp meter on the charging battery is only to show you that it doesn't add up to the rate of charge that's taking place in the battery. And we're going to get into the 1 ohm resistor experiment and all that in the kit. So then, so we're going to have a termination voltage, and then we're going to let it rest. And you're going to see a difference over time. I think initially we will just encourage people to not let it rest and then just discharge it again to get the baseline experience. Then you can go off and do that experiment where you add rest to it and see the difference. And you'll see a difference too if you're trying to rotate these batteries back and forth, which brings me to the next point. But at this point, I haven't shown you it, so I'm going to show you the actual motors running right beside the camera. So here, let's back it up a bit. Oops. All right, so here we've had the power supply powering the input at 12.47 volts at 108 milliamps, 1.34 watts. So there is 2 motors here, motor energizers. The one we're looking at is the input, or on the left side is the front one. And there's our circuit diagram there, or circuit board. So this battery right here is charging. This is the input from this power supply here. So this is the very basic setup. We have a generator coil powering this LED with a nice brightness there. So that will be one of 3 different LEDs that this can power at the same time. But this is the basic demonstration. This is the second demonstration here. It's also the same circuit powering an LED with the generator coil. But it has a capacitor pulsar, which is down here, thanks to Michael. He makes these circuit boards for us. And in this case, this is charging. This is more of a positive charge into this battery. This is becoming more of a negative charge. This one allows for the battery rotation. Now in this case, we have the amp meter showing not very clear. Under 140 milliamps on there. Maybe that's better. No, not very good. Sorry for this. I have a case over here so it keeps the noise down when I was... It's not very loud, it's just... didn't want to have any disrupting sounds. So, in this case, we have a nice easy board to work with. We do have a capacitance on the front end, and you'll understand about why we do that in the kit. So we have a nice little schoolgirl motor here that represents very similar to what the original Shami Bowman schoolgirl had. And again, this kit can allow you to do that original model with the same parts that she was using, do this model where you're charging a second battery, plus quite a few more modifications. And we're not going to get into that here in this video. So I think that wraps it up. This video is long enough. And the idea, again, as I said, we formed this battery right here This is the one. Actually, this was brand new. These ones are older. So this one we formed. This one we're not worried about right now. We're just looking at this battery for this test. So there's hundreds of tests that we can do, and I'll outline quite a few of them in the kit. But I'm just doing this so you can see where we're going to start with and go from there. So thanks for watching, and I hope you enjoyed.